Hello everyone. We'll start with lecture 5, which is related to mesh analysis. So we discussed before that now that we know Ohm's law, we can use Ohm's law and Kirchhoff's law, we can apply them to come up with a formalized way to solve circuits. That gives us two tools, which is nodal analysis and mesh analysis. Nodal analysis, which we've gone through, is mainly based on KCL, while mesh analysis is mainly focused on the utilization of KVL. So let's move forward now that we are familiar with nodal analysis. Let's have a look at mesh analysis. So mesh analysis is another generalized form for solving circuits in linear circuits specifically. And what we focus on here is to look at the currents within the mesh. So first we have to define what a mesh is. A loop is a closed path with no node being passed more than once. So that's what defines a loop. However, a mesh is a loop that does not contain any other loop within it. So if you have a loop that contains other loop within it, it cannot be a mesh. What this does for us, this new definition of mesh, it ensures that we always end up with independent loops. So basically meshes will always be independent loops from one another. So that's the main reason we have that rule put in there. There is one aspect of mesh that is limited, and that is the fact that it can only be applied to circuits that can be put into a planar format, so basically a 2D format. If you have a circuit design that requires a 3D representation, so basically one path is crossing another, then you can't really use mesh analysis. And that's why nodal analysis is a more favorable approach by industry, because today's circuits are very complex and you can easily end up with scenarios where you don't have planar circuits or 2D circuits. So let's have a look at what exactly I mean. If you look at this circuit on the left-hand side, what we notice here is that we have this 13 ohm resistor that crosses basically two planes. So basically if you tried to put this on a 2D design, you would have this line cross other lines. However, we can see that all these other circuits can be solved using mesh analysis. So the mesh analysis steps are as follows. Assign currents to each single mesh. So if you have n meshes, then you will have I1, I2 to IN currents that apply to the meshes. Apply KVL within each one of these meshes, so you will get n KVL equations, and solve these n equations accordingly. So let's have a look at an example. So for example, here's a circuit we're given, and we're asked to find I1 and I2. First, so we're looking at capital I1 and capital I2 are the two currents that we're asked to find, and I3 obviously. So our goal here is to use mesh analysis to solve for this circuit. So what we notice right off the bat is that, excuse me, what we notice right off the bat is that we actually have two meshes. You cannot consider this loop to be a mesh because it has two other loops within it. So we have mesh number 1 and we have mesh number 2. We assign circuit current I1 to this mesh and we assign current I2 to the second mesh. Please know that it doesn't matter which direction you select for I1 and I2. However, after you've selected the direction, you have to respect that direction and make sure you write your equations accordingly. So let's have a look at mesh 1. What we have here is we have I1, so we start circulating in this direction. So we have negative V1 plus I1, negative V1, as we have here negative V1, plus I1 times R1, plus I1, because this current is going the opposite direction, minus I2 times R3. And that should be equal to 0. Let's have a look at mesh number 2 now. If we go through mesh number 2, we have I2 times R2 plus, because now we're going across from positive to negative, it's going to stay as plus V2 plus I2 minus I1 times R3. So we're looking at the current going this way, and that is I2 minus I1 times R3 is equal to 0. Now we can solve for these set of equations now because we have two unknowns, which are small I1 and I2, and we can solve for that. And then at that point we can find capital I1, capital I2, and I3. Because capital I1 is going to be I1 small, capital I2 is going to be I2 small, and capital I3 is going to be I1 minus I2. So whatever you find, you can find those values. We'll solve some problems in class, but I thought we will now go through the concept of supermesh. So very similar to the scenario of nodal analysis where we had supernodes, we also run into the scenario of supermeshes. So when you have current sources that are showing up at one of the branches, then you may run into an issue. Now, if that current source is actually corresponding to only a single branch, if that current source is only affecting one mesh, then it's actually beneficial, because now we know, for example, in this scenario, we don't know what I1 is, so we have to write down the equations. However, we know what I2 is, because I2 going through this branch is going to be negative 5 amps. The reason it's negative is because this current is moving up, and the direction we selected for I2 is moving down. So in this kind of scenario, similar to the case of nodal analysis when we had a voltage source between a node and the ground plane, then it was easy to know what the voltage as that node was. If we're doing mesh analysis and the current source is only affecting or is at a branch that is not shared with any other mesh, then it also makes our life easier. So what happens if we have a current source that is shared between the two meshes? In that case, we have to form something referred to as a supermesh. So what we will do is we will join the two meshes together, construct a supermesh, and then we will proceed from there. When we are joining these two meshes together, we make sure that we remove the current source and any other element that is in series with it. So the reason we have to do that is basically here. The voltage across a current source is not known prior to the application of the mesh analysis. So when we are doing that loop around the mesh and trying to write KVL, well, we don't know what the voltage is, and that's the main reason we have to form a supermesh. So let's go over a scenario where we would run into a supermesh. So in this case, we have a current source, a 6 amp current source that is shared between I1 and I2. So now we have a problem because I1 and I2 are being shared here. So what we will do is we will form a supermesh. So we will remove this, and then we make sure that we maintain the proper labeling, and we then go around this one single mesh that is left. So in this case, we will have minus 20 volts plus 6I1 plus 10I2. You have to remember now you're entering the second part of the circuit, and the currents here are I2. Plus 10I2 plus 4I2 is equal to 0. So this is the equation that we get by looking at the supermesh. So now we have two unknowns on one equation. We also have to use KCL on one of the nodes. So we will apply KCL here, where we have I2 is equal to I1 plus 6. And at the end we solve for I1 and I2, and we will proceed from there. So we'll solve some problems in the class. Now, the next question is, how do we decide which approach to use to solve the problems that we need to solve? Do we use nodal analysis or do we use mesh analysis? So the answer to that question is determined by first looking at the particular network or the circuit that we're trying to solve using or analyze using either format. And the second factor that plays a role is what is the problem is asking us to find. Is it asking us to find the voltages at the nodes, or is it asking us to find the currents within the branches? So let's look at mesh analysis first and see what we would apply that to for. So if we have many series connected elements, we would use mesh analysis. If we have a lot of voltage sources, we would use mesh analysis. If a circuit that has fewer meshes than nodes, then again we would use mesh analysis. If we are trying to solve for the currents within the branch, so that would be the network kind of aspects of things, but what about the fact that what is the problem is asking us to analyze? If it's asking us to find the currents within the different branches, then again we would resort to mesh analysis. Mesh analysis can be used for transistor circuits. However, for amplifier circuits, we mainly use nodal analysis. So when I told you before that when you go to in microelectronics and you will end up using nodal analysis quite significantly, I would like to let you know that it's important to realize that a lot of times when we're building circuits with transistor, we actually end up with amplifiers. And in that case, we would use nodal analysis. And the main reason for that is that we would not know what is the voltage drop across the terminals of an amplifier, and we will get to amplifiers very soon. And so that's why we will use nodal analysis. So when we arrive at at the amplifier circuits, please make sure that you avoid applying mesh analysis. When do we use nodal analysis? When we have a lot of elements that are in parallel with one another. When we have a lot of current sources, because it makes our life easier. Circuits with fewer nodes than meshes. Now, if we move on from the network side of things, then if we have been asked to find the voltages at the nodes, we would again resort to nodal analysis. And then if we obviously have circuits that cannot be represented in a 2D format without branches crossing each other, or a planar circuit, a non-planar circuit, then we would resort to nodal analysis. And so overall, nodal analysis is what's mainly used because it's also easier to try to solve circuits using this format in computers. Now, I would like to introduce you to PSpice. We're going to have some projects using this software for circuit analysis. Basically, PSpice is capable of analyzing a circuit to complete details. And how it does this is by finding the currents and voltages at all the branches and nodes respectively. What you have to do is first you have to draw a schematic, which would be very similar to the drawing of the circuit that you have. And then you would indicate using viewpoints that you would like to know, for example, the voltages at certain nodes, and then you perform analysis and simulation, and you will find the answers. So if we look at, for example, this circuit over here, we can represent it as so in PSpice. And what you have is basically you have to ensure that you tell PSpice which node is your ground node. If you don't, then it will actually give you an error, but also because it doesn't know where the reference node is. Now, if you put viewpoints at these nodes, it actually calculates what the voltages are at these nodes, and you can easily solve and analyze the circuit. We will have some projects using PSpice for you. I thought it would be important for me to also introduce you to transistors. So there are two types of transistors: field effect transistors, or MOSFETs or FETs, and bipolar junction transistors. Basically, almost all the transistors that we're dealing with in many CPUs, LCD screens, and anything else is now field effect transistors. Bipolar transistors are mainly used in power applications and high power applications, but they're not used in very large scale circuits or VLSI circuits. Now, transistors are obviously three-terminal devices. This is an N-type transistor, and this is a P-type transistor. And we'll discuss in class what these are, but basically this is a layer of silicon. We dope it with, for example, different elements, and we will arrive at a silicon that has more electrons, or we arrive at a silicon if we dope it with certain material like phosphorus, for example. You will arrive at more protons, or holes as we refer to them in terms of microelectronics. So if you have only an MP or a PN junction, you will arrive at a diode, but if you have an NPN junction, you arrive at a transistor, and you can control the flow of electrons from the collector to the emitter using the base. So basically, by applying a certain voltage here, you can make this switch be closed, or you can actually apply voltage here and close or open this switch. So this is the whole concept behind transistors. We also have a PNP transistors, which is a P junction, and an N junction that is placed there. It has different applications, obviously, but we'll discuss a bit more in class how this practically works. But basically, by applying a voltage here, we create a tunnel which allows electrons to enter the N-doped silicon, pass through the P-type silicon, and then pass through the N1 and exit through the emitter. A similar kind of concept happens here but the current is now flowing in the up direction. The way you would know whether you have an NPN transistor or a PNP transistor by looking at this arrow. Obviously, when the current is flowing from the collector to the emitter, you have an NPN transistor. When you have a current flowing from the emitter to the collector, it's a PNP transistors. Almost 99% of the transistors that are used are NPN transistors, and so that's the kind of transistor that is used. We'll solve some more problems in class, and I look forward to discussing this and answering any questions you may have.